Are now live on YouTube. It's preparing to stream. There's going to be a little bit of a delay.
Okay.
Ryan's on the other end of that. Now live on YouTube. It's preparing to stream. There's going to be a little bit of a delay. And I can turn that off. All right. Okay. All right. Now let me make you host. See if we're still, okay, we're still live on YouTube and you are now the host.
Okay.
And I will stop my video.
Okay. And I'm gonna turn on my screen share.
Yeah.
And then my video as well.
Hooray!
Whole screen went away, but can you all see me and the slides and all of that?
Yes.
Okay,
that looks
cool.
Great.
Yeah, I'm very excited. I spent more time than I should have on the slide.
No, but it looks really fantastic. All right. It is noon. I am seeing a few more people dropping in. So do you want to wait another minute or two, or do you want to get started?
Oh, I'm happy to wait or start, whatever. You know, you can say when we start.
Okay. All right. Awesome. Well, yeah, let's go ahead and get started. We did say it started at noon.
Okay. So I just want to check real quick before when I move the slides, can you see that?
Yes.
And when I like point at stuff with my mouse, does that work?
Yes.
Okay, great.
Okay. I'll do an intro.
Okay.
Okay. Hi, everybody. Welcome to today's session. My name is Erin Burns. I'm one of the STEM librarians here at Texas Tech. Today's session is from Amanda Lobmeyer. She's presenting on SNAP, the math behind Thanos, or why Thanos was wrong. Dr. Lobmeyer is an assistant professor who joined Texas Tech in fall of 2020. She received her PhD in applied mathematics from North Carolina State University in 2018. Between 2018 and 2020, she was a postdoctoral fellow at the University of Nebraska. She conducts research in population ecology and works closely with collaborators in the biological sciences. I could keep going, but that is up to Amanda.
No, that was a great introduction. Thanks.
Yeah, expertise in developing mathematical models and leveraging empirical observations to address application level concerns. So, feel free. One thing just about our session today, this is part of the Science Meets Popular Culture series. There is a question or raised hand. You can use either one at the bottom. If you would like to ask a question, you should be able to click the Q&A button at the bottom of the screen. This will also allow other attendees to see your question and upvote them if they have the same question. We do also have a chat box, so feel free to use that as well. The chat box in our live stream today on YouTube is not available. But again, feel free to use the chat here in the Zoom session today. All right, now Amanda can take it away.
All right, thank you, Erin. So my presentation is about the math behind why Thanos was wrong. And so I had actually done a little introduction too, just to sort of like set the stage for the presentation. So hi, everyone. As Erin said, my name is Amanda. I'm an applied mathematician and I work in population ecology. But I'm also just a big fan of fantasy, sci-fi, and graphic novels. And so that's why I was so excited today to be able to kind of bring those two things together to talk about Thanos and his snap in the Marvel universe, but also kind of to think about it in terms of the tools I use in my research, which is mathematical modeling and analysis. And I just want to say that I promise that'll be fun. It can maybe be like a hard sell, but I'm going to make it as pleasant as possible for everyone in this room. I wanted to give you a few content warnings before I start my presentation. So there is just going to be no respect for Thanos in this presentation. If your team Thanos was right, then you're not going to get what you want out of this presentation, and I am sorry for that. I'm also going to reference and show images of franchise-appropriate violence because this is a discussion of a time when Thanos just like obliterated half of all people. And on that topic, this will contain spoilers for Avengers Infinity War and related like movies and comics. So if you had gotten to this point without knowing the premise of Avengers Infinity War and the end of it, I probably just spoiled it a second ago, but this presentation will be more spoilers. So please don't be here if that's something that you're not ready for. I'm also going to include a lot of GIFs, pictures, and memes just because I had a lot of fun putting this presentation together and finding all those things. But the first thing that I want to talk about is kind of the idea behind why is Thanos. So probably we're on the same page about the basics of Thanos. He kind of shows up in Avengers Infinity War. And when he's there, he's just beating up and killing off all of our favorite Avengers and assorted, people of the world. And who Thanos is he's from the planet Titan, and he's just been rolling through the universe, killing off planets full of people. But the why behind Thanos is the thing that's more interesting and worth talking about here. And sometimes like what he's doing is a little bit unclear, but he does monologue about it. So we have some evidence as to what he was planning. I want to be clear before I start that I'm not talking about this Thanos right here. So Thanos in the comics and Thanos in the Marvel Cinematic Universe had different motivations. Here's a couple of comic panels where Thanos is talking to, this right here is the Lady Death. And he's sort of apologizing to her. And then he very menacingly holds up his gauntlet and says he's going to do what he's supposed to next. And so in the comics, Thanos was infatuated with this personification of death, and he sort of collected the Infinity Stones and used his gauntlet for her affection and attention. And assessing the motivations behind that particular plan that's just outside my area of expertise. Thanos would be better evaluated by like a research or a relationship counselor in that situation. My personal opinion is that it was also a bad plan in the comics, but like I don't have any professional credentials that would back that up. But in the movies, we have this Thanos. And when he's describing what he's going to do next, he calls it a simple calculus. And he says that the problem is the finiteness of the resources in the universe. And so like resources, calculus, that is exactly in my area of expertise. And that's why this is the Thanos we're talking about. And I'm just going to give you a spoiler for the end of this presentation. What Thanos does actually is a very simple calculus. It's just that he did that calculus wrong. But the sort of motivation behind what Thanos is doing here is basically overpopulation. He says at one point that the problem is that there are too many mouths, but not enough to go around. And what he's saying there is basically there are too many people and there's not enough resources for those people. And so what he's seeing is overpopulation, and what he perceives is that it leads to suffering. When there's not enough resources for every person, some people are starving, some people are choking, just bad things are happening. And he describes that in the context of his homeworld Titan, where sort of pictured on the right here in this very grainy photo from Know Your Meme, sorry. But on the right here is his homeworld Titan as it used to be. And it was this really prosperous, technologically advanced place. It looks very peaceful and pleasant. It's got those big open green spaces that you like to see in sci-fi worlds and big blue skies, and then just all kinds of technology and big structures. But then on the left is Titan as it became. So the population of his homeworld overextended itself and it sort of destroyed the planet. It's left in this desolate state. And even like the gravity is messed up somehow, just they made a whole mess out of it. And at this point, Thanos is the only Titan left because the rest of his people died. And so this sort of event is what sparked Thanos to be concerned about overpopulation. And his plan at that time and for all time forward was to just cut the population in half. His reasoning is if you have half as many people, then anyone who's left over will have twice as many resources. And so then no one will suffer anymore. That's kind of like demonstrated in this picture right here, where you imagine if you're in a room, there were 3 chairs, but 6 kids that need those chairs. One course of action might be to say, okay, I guess I'll procure 3 more chairs. But what Thanos would say is kill half the children in the room, which is clearly not the appropriate course of action. But in the context of the movie, Thanos's motivation, and then like the way that he picked this plan to deal with that motivation were presented as sort of reasonable, if not sympathetic, but like he was a reasonable villain. And it also sparked a whole lot of conversation. So I gathered a few headlines when I just did a search for Thanos and overpopulation that came out over the years, just discussing this idea of how Thanos was concerned with overpopulation and what that means in the context of our world. And this one was even filed under climate change on the website where it was hosted. So it's an idea that kind of speaks to us quite a lot. And I do want to acknowledge that in his motivation, Thanos does have a fair point. I have these pictures that I just pulled from the Wikipedia pages on overpopulation and degradation. Here's some smog in the air. Here's some deforestation. And then here's some like pollution in a river. And the idea that human overpopulation, or at least overconsumption and overuse of resources, is degrading our environment is a real one. You can see real environmental impacts of the choices we make. And those impacts, beyond just degrading these resources that we depend on, also have real human costs. So when the quality of air is reduced, people who already have breathing difficulties, it's even worse. When water sources are polluted, like that's drinking water for some group of people. And so the problems of overpopulation and the consequences do have like a real basis, but it's just the way that he addresses them, I think, are wrong. So since I've acknowledged like the why of Thanos and sort of how I would be willing to meet him halfway with this is a problem that needs addressing, I do want to focus on why I think he's wrong specifically. So I made up this little brew meme that kind of demonstrates how I feel about what Thanos was doing. So the basis of his plan was he was going to pick up all the Infinity Stones and put them in his all-powerful gauntlet. And then he decided that what he would do with that is snap his fingers and get rid of half of all living people. But the problem that I see with that plan is that eventually, if you get rid of half of all people, they grew once, they'll grow again, and then you're just going to be in the same place eventually. And so this last panel right here is how I think Thanos would look like some point down the line when he realizes that what he did accomplished nothing in the long run. And to kind of build intuition for why this would be what happens after Thanos' snap, I want to just have you think real quick about how we as people feel about invasive species. And I would summarize the way that we approach invasive species is we kind of say any invasive species is too many. So for example, you could think about murder hornets. Those were a hot topic last year. Like start of 2020, we started to see articles about the murder hornets, and then they've kind of tapered off because in the wintertime, hornets and bees aren't active. But this article right here was actually pulled in the last week. We're getting ready for another season of murder hornets. And if you missed it the first time around, the idea with these is that they're a type of hornet that comes from not the US. And so when they show up here in North America, they are very good at their job, which is to destroy other insects. And so they can just like decimate native bee populations. And the like recommendation for what to do about murder hornets is just eradicate them. It says right here, they must be eradicated. If you read this article, it gives you recommendations for what to do if you see or suspect the presence of murder hornets. And it's like, put up traps to capture the murder hornets, call the officials to come destroy the murder hornets. That's all they say to do. It's never like, oh, if we could just get rid of some of the murder hornets, it would be okay. It's every single murder hornet is bad and must be gone. For another example, I also pulled this picture from texasinvasives.org, which is just a website that came up when I searched for zebra mussels, which I had been hearing about in the news recently too. And so the idea with zebra mussels is that they can be introduced to a freshwater source, and then they sort of flourish and can choke out native species. And so they're bad to have there. And they're very easily like transmitted between different lakes, for example. And so just this website kind of sets the tone for how we treat invasive species. The tagline is "Hello, invasive species, goodbye, Texas." Like the presence of invasive species will take away your entire state. And then these graphics that they make for dealing with the zebra mussel, it's like you need to protect the lakes you love, stop the zebra mussels. And a zebra mussel is this tiny thing, but it's very dramatic and stark, the way that we talk about them. And the specific advice they give is to clean, drain, and dry. And those actions are to sort of, anytime you might be transporting water between different sources, just make sure that you get rid of all that water. don't let it go anywhere else because zebra mussels might be inside of it. And if they are, you would be spreading them to places they haven't managed to sort of infest yet. And the advice is never like, it's okay if you forget sometimes, just do it whenever you can. It's every single time a boat goes in the water, get rid of the water before you take it somewhere else, because you might introduce zebra mussels. And so in both these situations, sort of what we're seeing is the way that we deal with invasive species is in terms of eradication and management. We don't want to introduce more of these into the wild. Whenever we can, we want to destroy them. And then if we can't do those two things, the problem might not go away. If invasive species aren't really your thing, you could also think about this in terms of pests that are in your home. So the example I've got on the slide is a bed bug infestation. So a house infested with bed bugs or a hotel infested with bed bugs is sort of how Thanos sees the planet Earth. Just we are the bed bugs in Thanos's house. But if you had a building that was infested with bed bugs, you wouldn't necessarily think that getting rid of half the beds would sort of like, oh, now you have fewer bed bugs, so eventually those bed bugs are just going to go away. That would never be a solution. That's what Thanos' solution was. But if you look at how people actually deal with bed bugs, it's more along these lines. So if you read a guide, it's like you need to have an industrial oven that gets everything you own to a particular temperature. And then probably you want to put it in this like vacuum in space for a couple months just to be safe. And then even then you might still have bed bugs, like just there's no way to get around the bed bugs. And both of those ideas, either the bed bugs or the invasive species, sort of comes down to what I'd call an exponential argument, which is that if a population grows really quickly, then whenever it suffers a sudden loss, it's going to recover very quickly. And the reason it's called an exponential argument is because it's describing something called exponential growth. And exponential growth just means the larger you are, the more quickly you grow. And so right here on the right-hand side of this slide, I kind of have a picture that I just pulled from Wikipedia of a couple different lines. And the red line right here is linear. So imagine that this horizontal axis is time, and this vertical axis is population growth. And so linear population growth would be like for every 5 you step sideways in time, you go up 250. When you go up to 10, that means you would reach 500. You kind of always have the same amount of growth. This middle line right here is a cubic function. So it's more shallow than the linear function to start, and then it kind of like picks up more than the linear function by the end. This green one, much more dramatic than the cubic function, is an exponential function. So it's given by this equation, f of x equals 2 to the power x. And the behavior it has is it starts out really low. So along the vertical axis from 0 to 5, maybe like 0 to 5 years, not much is happening for the size of this population. It's way below the red line. But then in the last 5, it takes off really high. And the reason for that is because the growth depends on the size of the current population. So down here, the population is really small, it's growing really slowly. But by the time you get up here, the population is really big. And so just between 9 and 10, you're going to have this huge jump because of how large the population was. That's what exponential growth means. I thought it would also help to kind of see a video of how exponential growth works. So this is a petri dish of E. coli in a lab. And sort of they've been growing really slowly while I've been talking, but they're starting to pick up a little bit more. And then in this very end of the video, just they take over the whole screen. So let's watch it again now that you know that's the end story. In the first 100 minutes, almost nothing has changed about these bacteria. In the second 100 minutes, sort of, they've grown to that size. But then these last 100 minutes, they do more than they did in the first 200 minutes combined. That's, again, exponential growth. Sort of down here is our first 100 minutes, up here is our last 100 minutes. And the reason I bring this up is because if you look at a plot of human population growth from like 1800 to now, it looks about exponential. Like there's some problems with this, but it's a good place to start our conversation. So here's a diagram I took from the Wikipedia page on the world population, but the data is actually pulled from the UN's population tracking. So what it's looking at is from 1800 to 2020 is where the data actually is. And if you just look at that part, this gray part of the line, the shape of this looks like that exponential curve. It's really shallow at the start, and then it picks up really quickly. At the end, it's kind of more linear, but approximately this is an exponential curve. And I really want to focus in on what's happened to our population in the last 50 years, between 2020 and 1970. And so in that period, you do have this approximately linear growth, but it's very steep. So I went ahead and just pulled that data by itself from the UN. I've got 2020 over here and 1970 over here, and this orange line is the change in our population over that time. But looking at this plot, it's the population in billions along the y-axis, the years along the horizontal axis. It's really hard to have intuition for what's happening here. And so I thought I would put it in the context of the population growing as we move through events in the Marvel universe. So first point on the plot is 1970. That's the year that Tony Stark and Steve Rogers went back to in Avengers Endgame to get more Pym particle. And Steve Rogers had a chance to see Peggy Carter, and Tony Stark had a chance to talk to his dad, who was on the way to see his pregnant wife. So in 1970, when that happened, the population was 3.7 billion people. That's a big number, but it's not as big as we're going to get to by the end of this. Forward 10 years is 1980. You've just seen a little bit of change. We're up to 4.46 billion people. That's when Star-Lord's mom and dad were hanging around in, I think, Missouri, in one of the Guardians of the Galaxy movies. Forward 15 years to 1995, the population's at 5.74 billion. That's more of a jump than we saw the first time, but that's because we went further. We're still about the same rate of growth as before. And that's when Carol Danvers crashed the real blockbuster video in the Captain Marvel movie. Then up another 15 years to 2010, we're almost at 7 billion people. That's when the Bruce Banner that never was would have first become the Incredible Hulk. And then 2018, that's where Avengers Infinity War took place. That's when Thanos snapped his fingers and got rid of half the population. And during that year, the population of the planet would have been 7.63 billion people. And so after Thanos snapped his fingers, if you've been like keeping track with the numbers all along, he would want to take it down to 3.8 billion. That's getting rid of half of 7.6 billion people. But all that does is turn back the clock to about the year 1972. So after Thanos snaps his fingers and destroys half the world's population, what he's done is he set us back to the year 1972, which is like Tony Stark would have been making sentences for the first time, and Nick Fury would have already been doing spy stuff during the Cold War. So it's really not that far back in the past to go from 2018 to 1972. And that's all that his snap accomplished. That's just several years, really. But sort of one argument is that in 1972, we didn't know everything we know now. So Thanos did turn back the clock only 46 years, but now we know more. So if we started our population at that point, we could make different choices and change things. And I decided to do like a little history search to see how valid that point is. And here's just a couple like random dates I pulled. The Sierra Club, which was sort of established to preserve wilderness in the West, was founded in 1892. They're still around today. By the 1950s, they had already expanded to thinking about issues of pollution and resource exploitation. The tragedy of the commons is like a common talking point, and it was first like formed in 1833, and it was popularized in 1968. And the fundamental idea is that when we have common resources, kind of like the air we breathe, then we collectively suffer because there's no like motivation for individuals driven by self-interest to preserve that resource. So it's very much like an environmental argument about why the world itself is not preserved by the actions we take as individuals. But it would have been known in the 70s. And then the EPA was actually created in 1970 in response to human concerns about like pesticides and chemicals that we were introducing into the environment. So that was more of a like hot or a new topic in 1972. And I also went ahead and did like a Google Scholar search for just the word overpopulation between 1970 and 1975. And so this isn't an exhaustive way to see how much this was a conversation in the 70s. It was just sort of one quick way to check. And there were 7,500 results. There would be more results if you check today, but we do a lot more science today than we did back then, like more quickly. And then the first article, though, is this paper talking about the Mesopotamian concept of overpopulation. I think it was first just because I had a lot of citations. But so not only were we talking about these ideas in the 70s, but part of talking about these ideas in the 70s was talking about how people were talking about this in Mesopotamia. So it's not a new idea, overpopulation. It's definitely something we were aware of in the 70s. The second article on this Google Scholar page, which didn't fit into the screen cap I had right here, was actually titled "Nobody Ever Dies of Overpopulation." And I admit, I got a little bit nervous when I saw that. I was like, oh no, I'm this far into my presentation. I already promised I was going to do it. And I didn't even check if the 70s were a different time was a valid argument. But I downloaded the article, and right here are the last like 2 paragraphs of it. And I'm just going to summarize what the author is saying. They kind of say, well, what would we say if the power shut down in the middle of summer and people died of heat? Would we blame the weather or the power companies for not being able to keep people cool, or the environmentalists for saying that we needed to deal with pollution? And then they sort of end with this idea that the one thing we wouldn't do is blame overpopulation, because we never blame overpopulation. And so the end story of this article isn't that nobody dies of overpopulation, but that we blame other things without changing the underlying behavior that leads to the suffering we see. And something that really struck me when I was reading this is this first paragraph is just so similar to conversations we were having earlier this year during that really cold snap we had here in Texas. We had the power couldn't be sustained for people during this very cold time, and people were suffering because of it. We were like, well, what are we going to blame? Oh, the problem is the weather was unexpectedly cold. Why was the weather unexpectedly cold? Or we blame the power companies for not having the infrastructure. Why was that allowed to happen? Or there were some people who blamed alternative energy sources for not being able to sustain the people, but alternative energy made up a very small amount of the energy that we actually needed to stay warm during that crisis. So just the fact that these talking points that the author is sort of discussing in 1971 are the same talking points that we're talking about in 2021. I would argue that if you set the population back to 1972, there's no real evidence that we would do something different at this point. And then if that's not convincing enough, I would say like human pettiness would keep us from doing something differently if our population was suddenly set back to 1972. Because another thing that we didn't have in 1972 was like a giant purple villain who had just dusted half of the people we care about. So sort of in response to Thanos destroying half the universe, in the Marvel Cinematic Universe, what they did was they made a big memorial in San Francisco, and then some of the Avengers were like, we're going to go fight. But there wasn't a single person who was like, I don't really agree with Thanos's methods, but he had a good point. So we should probably just do what he wanted and keep the population at this level. Like, that just wouldn't happen. People would be too angry to do that thing. So sort of in summary, I don't agree with Thanos's plan. As far as the implementation of his plan, he worked on it for at least 20 years, and I think it was probably longer. I got 20 years because he described the plan to Gamora shortly after massacring half the people on her home planet. And she would have been 29 at the time of the snap. Probably she was under 10 when that conversation happened, so he's been working on it for 20 years. But Thanos was like 1,000 years old at the start of Infinity War, so he's probably been thinking about this longer than those 20 years. And the length of retirement that he's bought himself on the planet Earth is 46 years. He took 2018 and shifted it back to 1972. So just in terms of like what he got for what he did, he worked on this for 20 years. He got about 2 years for every year he spent working on it. And that's why I rate his plan a 2 out of 10. He definitely did something, and it's unfortunate for everyone on Earth, but it's really unclear what he personally accomplished. Like, he sits there and he looks very happy with his retirement on his farm on this very nice planet, but it's just a waiting game at this point. And given that his lifespan is in the thousands of years, buying himself 46 years on one planet is just sort of a drop in the bucket. So yeah, now that I've argued why Thanos was wrong, I'd like to kind of spend the rest of the time I have talking about why Thanos is bad at math specifically when he's wrong. Kind of everything we've done up to this point has been more intuition about why he was wrong. But it would be fair to ask, how do you know that that's what would actually happen? And the way we're going to address that question is through mathematical analysis. So I picked like 5 different topics that we're going to use here. We're going to describe the world using math. We're going to take derivatives, talk about differential equations, stability analysis of those equations, and then bifurcation analysis of that stability. And all those words sort of going down the line from describing the world down to bifurcations, that would be sort of advancing in like more difficult math classes. And so at this point, you might be sitting here and you're like, oh no, I signed up to listen to a math talk. Like, what was I doing? So I just want you to like, please don't worry. If you're unfamiliar with those topics that I named, or even if you've heard of them before but haven't thought about them in a while, that's fine. The core reasoning behind everything that I'll talk about here is probably familiar to you, because math is kind of developed to describe human intuition and thinking. So it's all the ideas should click. And if the symbols and like graphs and stuff start to intimidate you, just try to like not zero in on what you don't know, and instead think about what you know would happen like intuitively based on what you know of the world. And so we're going to start with that first point, describing the world. And we came up with lots of different ways to describe the world when we were doing that first section on exponential growth. The video of the bacteria growing is a description of how things happen. The plot of the human population is a description of how population changes. But if we want to mathematically analyze the descriptions we have of the world, those descriptions have to be written in a mathematical language. And so the closest we got in that section was when we had this graph right here, and we were able to like write equations for the different lines on this graph. And so we're going to be talking about this exponential one, that f of x equals 2 to the power x. That was the thing that looked like this green curve, which sort of looked like our population curve. And I just want to sort of pull apart what's happening in this description. So this is a mathematical description, f of x equals 2 to the power x. What it says when you read this equation is, I want to tell you something about this thing f. That thing f, I think, depends on this thing x. And the rule I have for that dependency is this specific amount, 2 to the power x. The reason we do things like this is because what we'd like to be able to do is to say, if you hand me any number x, I could go ahead and calculate f of x. To put this in the context of what we've been talking about, the thing we want to describe is population. We think it probably develops in time. So as time goes on, populations change. And the specific way that we've decided this change occurs is exponential. We think that there's some rate, we take it to the power time, and that's how the population changes. And so the reason we would do this is so that we would be able to say, okay, if you hand me time 2018, I can calculate the population at that time using this formula right here. And then this was all using words, just to be really clear what we were talking about. But to kind of abbreviate it in an easy to use mathematical formula, we would write this. This P is our population. It still depends on T time. And then this is the specific way we said R to the power T is just the same as rate to the power time. And that's the same as when we said f of x equals 2 to the power x. I've just sort of reframed it in terms of what we really care about here, which is a population. So first step down, we described the world. The next thing we're going to do is talk about taking derivatives. So I want you to think back to the first time I kind of talked about Thanos's motivation. And I showed you this GIF of him saying, it's a simple calculus, the universe is finite, its resources are finite. And I was going to show you that his simple calculus is wrong. So the specific calculus we're going to use is derivatives. Derivatives are something that people would learn how to take in their first calculus class. And if you haven't thought about derivatives recently, or you never took a calculus class, I'm just going to talk through what a derivative is real quick. So derivatives represent rate of change. That's the easiest way to think about them. And mathematically, we represent them with symbols that look like this. So this first one right here, this df over dx, that's just a shorthand way that we indicate the idea of saying change in f over change in x. And the best way to think about derivatives is in terms of physical things that you're familiar with. So let's think about this car that's driving down a highway right here, this little blue one. So if we want to keep track of the car's location, we could kind of measure it right here in the picture. It's at location L at some time t. And then a minute later, it could proceed down the road and it would be right here. And we would be able to measure its location L at some time t plus 1, just 1 minute later. But the car isn't just changing where it is. The car is moving forward with some speed. And so speed is actually going to be the derivative of location. Speed tells you how you change where you are over time. It's this, like thing that shows up on a dial inside a car. It's telling you the miles you travel per hour. So change in location, miles per unit time, hour. And we would represent it in terms of these symbols as dl dt. So a derivative is basically speed. So for like a population, P, we know how to write an equation all the way back here, P of T equals something. But you could also think about dP dt being the change in the population or sort of its speed as it grows. And so now that we have that like basis for what a derivative is, we can go ahead and try to work through Thanos' simple calculus. So here's our original description for exponential population growth. We had that P of T is equal to R times T. We can go ahead and compute its derivative. The actual process for taking the derivative is something you would learn in a calculus class, but the outcome would be you calculate this quantity dP dt, and all that means is change in population. So it's telling us if the population grows or declines, basically. And the formula for calculating dP dt would be given by this thing right here. And I know it looks intimidating because there's that like ln of r hanging around. That's just a number, so don't worry about it if you don't know what that thing is. Really, the important takeaway is for like a positive growth rate, this amount over here is always going to be positive. So you have population growth because its change is positive. That means it's increasing. That means like if you have 10 people today, you expect to have more than 10 people tomorrow. And one thing I want to kind of like draw your attention to is the fact that this r to the power t, if you remember, is what we said p was given by to start. We said p equals r to the power t. So we could go ahead and say that this formula, instead of dP dt equals ln r RT, is actually dP dt equals ln r times p. I know it's a lot to think about, so I just want to like re-emphasize real quick what that equation I just read off real quick is saying. Oh no, is the current change in the population, dP dt, the derivative of the population, is given by some random number, don't worry too much about what it would be, times the population. And that tells us quite a lot about the population already, even if we don't necessarily realize it right away. Specifically, the population growth is going to be faster whenever the population is higher. If this number is the same, then whether you plug in one person versus a million people is really going to change how big you say your current change is. That's sort of the same idea we had behind exponential growth. So if we have a group that Thanos is snapping his fingers for, and they're already close to overpopulation, that means that the current amount of people P is going to be really big. When you split that number in half, you're going to have half of a really big number, which I would argue is still really big. The difference between 7 billion and 3 billion people, like, yes, 3 billion is smaller than 7 billion, but it's still higher than I would ever want to count. So the growth after the snap is going to depend on half of your really big population. And it's still going to be a really big number. And what's going to happen is that it's going to depend on how large the population was to start. And the higher the population was, the faster they'll grow afterwards. Which means that Thanos' plan is going to work the very worst on the planets he most wants to change. If there's a population that's already like overpopulated, there's a whole bunch of people there, then when Thanos snaps his finger, there's going to be a whole bunch of people still because he only cut them in half. And then they're going to grow very quickly according to how many of them there are. And the recovery time that you saw, you know, ours was 46. If we had started at a higher population, the recovery time would be even shorter than 46 years. If he had snapped us back in like 1850, our recovery time would be much longer than that. And so that's where my sad Thanos face came from. This is Thanos's face, you know, in the middle of his farm retirement when he's like, oh no, this didn't work at all the way I planned. So that was calculus, taking derivatives. Now we're going to shift gears and talk about differential equations, which students will affectionately call diffie-Qs. A differential equation is sort of a way that we describe the world in terms of the way it changes instead of direct functions. So thinking back to this picture we had of the E. coli growing exponentially, it's really intuitive to ask, how is the population changing right now, really quickly? It's less intuitive to say, okay, look at this picture and then come up with a function P of t that does exactly what this population is doing. And at its most basic, a differential equation is just an equation that uses derivatives because it's in terms of change and derivatives represent change. And the thing is, you probably already know some differential equations. So I have a picture right here of like a shirt that a lot of kids used to wear, that it's like, it's talking about F equals ma, Newton's second law. And that formula is one that a lot of people know, F equals ma. But that is frequently a differential equation. That's force is mass times acceleration. But speed is a derivative of position. And I'll just tell you, acceleration is a derivative of speed. So that F equals ma is something that uses derivatives. And if the forces at all depend on speed or location, F equals ma becomes a differential equation. If you didn't know that one, there's this equation we used earlier, dp dt equals ln of r times p. Again, that was just that thing where we said the change in the population is some number times the population. But it's an equation, it's got a little equal sign in it, and it has a derivative in it. So we have ourselves a differential equation. Even if you knew no differential equations coming into this presentation, you now know one. But like the question you might ask yourself is, what will we use these equations for, even if you can write them down? And the answer is, first we could think about stability. And I want to give you an intuition for what stability tells us. So hopefully you've bought into this idea by now that derivatives tell us rates of change. So differential equations tell us about how things change because they use derivatives. And stability is something that's going to tell us about when a thing stops changing. And the example I want to give you is from Newton's law of cooling. Don't worry about the content of this little text box if you're not already familiar with Newton's law of cooling. Basically, it's a differential equation that tells you how temperature changes with time. And like the story is that it's going to change more quickly the further away it is from room temperature, and it's going to head towards room temperature. Stability is sort of what tells us when you put a cup of hot coffee on a table and you just wait a while, it's going to eventually reach room temperature. At the start of my presentation, I had my coffee right here. I've been talking nonstop, and so it has cooled down and is unappetizing at this point. That's something that you probably have physical intuition for, and it's exactly what you would get if you analyze the differential equation for how temperature develops. And the thing is that you do have great physical intuition for stability. Another example you could use is, here's a little curve, but imagine it's like a slippery hill, or just like there's something with wheels sitting on different points on this hill. So you would say, okay, if you're at point B, you're going to head down real fast and then kind of like, you know, balance out down here at the bottom of the hill. If you're here at point D, you'll do the same thing. But if you're up here at E, maybe you could be pushed in the other direction down that next hill, or, you know, backwards into the bottom of the first hill we were talking about. That sort of thing is an argument about stability. Where does the object stop sliding? Where do you end up when you're rolling down this hill? And we just use derivatives and differential equations to kind of answer this question more abstractly, so that when our physical intuition starts to fail us, we kind of have equations that tell us what happens. And to demonstrate this, I'm going to talk to you about non-exponential populations. So the truth is that exponential growth is actually a pretty bad population model. When I teach mathematical ecology, we like talk about that model for a minute, and I'm like, but really, let's think about what happens in the real world. So we're going to give Thanos' plan a chance with a slightly better type of model called logistic. So here's a picture of our exponential model, that thing that always goes upwards. Logistic just says maybe you start out acting like that, but eventually you're going to kind of level off. And the way it's formulated is you say the growth of something depends on how many resources it has available. Sort of the environment can only support some number of people, and then after that, no more people would survive. So you have initially the people can grow very quickly, but then as they reach that limit, that carrying capacity of the environment, they start to level off. And this leveling off could be described by a couple different biological things. Either you can't collect enough resources, so you start to have lower birth rates because you're just not fit enough to reproduce, or more dramatically, you stop being able to collect resources, you're directly competing with other people for the things you need to live, and so a lot more people are dying. One of those two things is correcting the population's growth so that it levels off. And the differential equation that describes this type of curve would be dp dt equals p times 1 minus p over 100. Real quick, the left-hand side is still the same as before. We're looking at change in population. It depends on the current population p, just like our old one did, dp dt equals something times p. But now that something is actually the distance from the number 100. As you get closer to 100, the change starts to slow down. You grow less. And that 100 is the carrying capacity of this population. It limits out right here at 100. And so I want to talk about sort of what happens when we plug in different numbers to that equation. If we plug in 100, that's just our dp dt equals 100 times 1 minus 100 over 100. You'll get 0. So the change in population is 0. So if the change in population is 0, it's not growing or declining, it just stops there. That's kind of the same as getting stuck at the bottom of this hill. So for this picture right here that we thought about earlier, this point C, you could think about being the logistic population has reached 100. It stays right there. It's not going to do anything else because that's where it tends to go. But if you think about being at 98, just a little bit before reaching 100, maybe that's a population that Thanos sees as reaching its limit of what the environment can support, and so he's going to snap them away. Their growth before his snap would have been 1.96, so about 2. So the growth rate, dp dt, is 2. So the population is growing. It starts right here, and it's heading towards reaching 100. And probably it would stop at 100 because that's what we saw previously. But then Thanos snaps them, and it moves them to being 46 people instead of 98. The growth rate then would be 24.84, so about 25. Compared to our growth rate of 2, 25 is a really big growth rate. So they're still growing, but now imagine them being higher up on this hill. It's a really steep decline for them. They're heading down very quickly. But they do still have the outcome that they would go down this hill, travel down to the bottom, and get stuck at 100. And so that's what you're going to find for any population lower than 100 that still exists. And Thanos' plan is still no good here. When he snaps the population down to half of its carrying capacity, it's actually going to be in this region where it can grow very quickly and recover and head back to this period where people are competing for resources and potentially dying because of it. And that's sort of the basic idea behind stability analysis. The carrying capacity is what's called an equilibrium value. It's stable, and it just means the population is always going to go back there, the same way that you would expect to slip to the bottom of a hill. And at equilibrium, the different forces that act on the population, their tendency to grow and their limits of the environment, they're just balancing out. And the thing is that equilibria and stability are just an idea of balance. And that's exactly what Thanos said he was all about. He just had a fundamental misunderstanding about how it works. The last thing that I'm going to speed right through is bifurcations, because we're getting real close to 12:50 and I don't want to go over time. And it's mostly pictures, so don't worry. We're kind of at the most advanced of the math classes that I'll talk about here. And so I'm just going to talk about ideas, and the equations and diagrams might be intimidating. Try not to let them bother you too much. But if we wanted to get even more accurate in how we describe populations, we could talk about them interacting with each other. So we can actually solve 2 different differential equations at one time, sort of describing how a population grows but also how that affects the resources it depends on. And here's a picture of a set of equations that does that. It's intimidating, but it's just the top one is change in resources, and the bottom one is change in population. And the change in resources brings back our good friend logistic growth, but then it says somehow the resources are getting used by the population, and somehow that leads to growth of the population. Population might die off due to old age. When we generate solutions to this type of thing, because we're thinking about two quantities instead of one, we look at them in a different way than before. And so we look at the comparison between the size of the resources, that's vertically or horizontally, compared to the size of the population, that's vertically. And kind of the arrows and lines on this figure show you the different paths that our system could take to reach its stable equilibrium. The place it's sinking to right here is its equilibrium. And all of the arrows kind of point like, okay, if I started with one resource and one person, I would curve around, do this thing, and head down here. But since we're down here, that's where the population is 0. So basically, this is describing extinction of people under this model. The thing is that the equations itself depended on a lot of different like letters and numbers. That's probably why it looked maybe intimidating if you're not looking at this type of model frequently. There's R, K, C, B, and M all hanging around. And each of those things could have a different value. They're not really known when I just put this jumble of letters on the screen. So if you just pick some different letters to use, you can get a different shape of the curves. And so here's just an outcome for different like values of population growth. And now, instead of heading down towards this value where everything went away, if you start with one resource and one person, sort of the people start to grow and we use up the resources. And then it's like, oh no, there are too many people, not enough resources. The people start to go down. And then once the people go down far enough, the resources can start to recover. People start to grow again. We're in this cycle where people sort of like oscillate around what is their equilibrium value, but it avoids extinction. And studying how these two different outcomes can emerge from the same type of equations is called bifurcation analysis. And it's basically saying different numbers that you plug into your equations that describe change can lead to different outcomes. So we had like our nice swirly outcomes over here. We can also have some extinction outcomes over here. And I don't want to hover on that figure for too long because it looks like a mess if you don't know what it's showing. The basic idea is that equilibriums, like where your cup of coffee goes at room temperature or the bottom of the hill that you tend towards, those long-term outcomes, they can change. But they only change if you change the underlying parameters of your equations, or that is the biological behavior of what's happening. So what Thanos should have done is he should have used his all-powerful snap to modify behavior instead of just reducing abundance. That would have accomplished something. Oh, I don't know why I did that. But if you sort of like go down the bifurcation rabbit hole further, that leads to that like popularized idea of chaos. There was that guy in Jurassic Park, he was a chaos theorist. Chaos is the study of really weird behaviors that come from this idea of changing underlying values to drive outcomes. So if that's something that's cool to you, look forward to that in the future. But sort of these 5 different tools of mathematical analysis we talked about, just in summary, they all point to the idea that Thanos was wrong. The 2 big takeaways I would give you are that changing where a population is doesn't change where it goes. So cutting the population in half doesn't change that they'll reach the same value eventually. The equilibrium of that population hasn't changed. The only way that you can change the population is to change its underlying behavior. That's that idea that something like the growth rate or the death rate or how much you consume has to change to adjust where the equilibrium is to avoid like extinction. And kind of like the reason that this is so exciting for me to talk about is because all those same tools we used for Thanos' silly little problem are the same ones we can use to study like real world populations and problems. So if that's something that's interesting to you, mathematical analysis and modeling is a really exciting area to kind of learn more about. So I thank you so much for your attention. I'm happy to answer any questions. I have this comic that somebody in my graphic novel club wanted me to include here of Dr. Doom like pulling the skeleton out of Thanos, but it's math that's doing it to his dreams instead. So thank you all for your time.
Okay, hey everyone, this is Erin. I do realize that there's also a possibility that there was chat or Q&A. Oh, we do have a Q in the question. Okay, perfect. Okay, so Carol is asking, overpopulation and lack of resources are the crux of many sci-fi movies. Basically, they have it all wrong because they don't address the underlying behavior. This is very interesting. I guess that was more of a comment.
Yeah, I think that's a good point, Carol. And I mean, like sometimes, you know, it's like a Band-Aid, I guess. He did buy 40 years for us. I mean, buy for us. It was a negative event and not good. But yeah, without changing the underlying behavior, sort of nothing's going to happen. Is the mathematical answer to Thanos's plan.
A couple people in the chat say, giving you applause and saying thank you.
Yeah, thanks, y'all. I'm going to drink my cold coffee while waiting to see if there are questions.
Yeah, if anybody else has got any other questions or comments, feel free to type them in. I do appreciate your use of GIFs. That was awesome.
Yeah. I'm sorry I crammed all that math in the end. Probably there's fewer questions because that part was just like too much. I tried to do too much in the time I had. So I know it can be a little overwhelming.
Yeah, I am not a math person. It did feel a little overwhelming, but it was, no, it's okay. But I knew that going into this, so I am okay with that. So we have a question about showing the bifurcation diagram for the logistic map.
Yeah, so I don't have that here. Hold on. I'm trying to exit my presentation and just open logistic map. Bifurcation. It's such a classic example. So I'm sure there are lots of images on Google. Let's see. Can I share that? Yeah. Okay. So this is like one of those examples of chaos. So here's the bifurcation diagram. Can you all see this?
Yes.
Yeah. So basically, like the idea of the logistic map is it's something that happens in discrete time. So it's unlike everything that we talked about here. But kind of like as you change that parameter of interest, you can change from having one expected outcome to like two that you bounce between to just like having these ridiculous trajectories. And I actually have my mathematical ecology textbook on my desk, so I can show you some of those different trajectories by holding it up to the camera like a terrible person. So like here's one of those where it bounces between two values always.
Yeah.
But then you shift the population just a little bit and it's going to do this just out there thing.
Oh, wow.
Just bouncing all over the place. So it's a really cool thing. And there's actually a video that describes this. Erin, it's one of the things I linked you for the lib guide when you asked. So it's, if you look up like logistic, let's see, logistic YouTube. It's giving me homework solutions. Here we go. Can I post to the chat? Is that allowed?
You should be able to. Just make sure it says panelists and attendees.
Okay, there we go. That's a video that kind of talks about this map that Matthew Hogan brought up for us. The video I think is a little bit like sensational, but it still gets to like some really cool ideas. And then, sorry, I just got to the chat. Carol asks if I silently yell at movies when they make these kinds of mistakes. Like they yell at historical films in movies. No, usually I'm like happy to kind of take it the way it comes. I'm like, oh, you know, they're just having fun with it. The one time I've yelled at a movie is in, I think it was Contagion, was like an infectious disease movie. And they're talking about R naught, which we're all familiar with at this point, but back then we weren't. And they write it like with an underscore on a whiteboard. Like that's how you would type it, but you wouldn't write it. And I was just like, who let this happen? That's the only time I've raged at math in a movie. Yeah.
Okay, we do have another comment in the Q&A section. This is from our previous presenter, Michael Sarah. Great job, Thanos' plan seems so intuitively right, but we really loved hearing the argument that he would just be turning the Earth back to the 1970s population-wise.
Yeah, thanks for that, Michael. I honestly didn't know that that's the level it went to until I started putting this together. And then I was like, wow, that's no change at all. It was really surprising to me personally.
Oh, okay, now we've got another one. Great
Sorry.
presentation. The children of Thanos included wizards, brutes, intimidating type characters. Seems Thanos would have been better served to pick up an intimidating mathematician. What would you name, what would your name, would you give for a math-based supervillain? So what name would you give to a math-based supervillain working for Thanos?
Oh man, okay, that's really hard. It's hard to sound intimidating using math words. Asymptote, I think, is a word that a lot of people don't like. So I want to work in asymptote. Man.
The accountant.
I can't do this on the fly.
Yeah, if anybody's got anything in the chat, feel free to type it in. Michael Sarah says the accountant.
The accountant, yeah, they're accounting for all life, and then there's too many in the red. I like that. Yeah. I don't know. I should probably like work on some superhero sounding like punchlines too. Like, oh yeah, I'm gonna bifurcate you or something, and then work those into doing math every day. Really keep things fun.
Let me see. Let's make sure I got that. Okay. Kimberly says, this was so interesting, fantastic slides. Non-math person here. So when you're doing literature reviews with mathematical topics, how do you go about that? Kimberly is one of our other librarians. Mm-hmm. You gave the quick example of using overpopulation as a key word. Are there other typically concepts you search with? What do you do when you have an equation? Yeah, so doing lit searches is hard in every topic, I feel like. So when I'm searching for things, I have to like balance, I guess, because I work at that interface of math and ecology. So I have to look for the ecology words like I did in that example of overpopulation or other things that I'm concerned with. But then like as far as searching for types of equations, usually you search words that describe the equation. So that way that I said, the logistic map is for discrete models. That's a word that describes a way an equation is formulated. So you learn the words that sort of characterize your equation. Like this is my chocolate ice cream versus my apple pie. You can't search for equations themselves because it's kind of hard, but people have the language to describe the tools they use, I guess. But it's hard. And then Matthew has pointed out archive is where people post like preprints of math papers. So it's a good place. I tend to use Google Scholar because I'm terrible. And I like how it lets you see like who cited that. So then you can like move forward in time from all the like classic literature to what people are doing. Mm-hmm. But archive is great for like new works and old works too. I've really appreciated all the engagement and questions, but Erin, I do want to be sensitive. I know that when we were ending— We are a little over time, yes. Yeah. So we'll just go ahead and I guess end it here. Thank you guys so much for being with us this whole time. If you have any questions, comments, concerns, please let us know. If you have a project in mind that you're working on that intersects science with pop culture, you can also let me, Innocent Awesome, or Rob Weiner know as well. We are looking forward to fall and picking some more sessions. So thank you so much, Amanda. That was awesome.
Yeah, thank you. And thank you all for being here.
All right. Have a good one, everybody.